Hey everyone, this is Connor Mead with the Calculation Center with another video in our calculus series. This time we'll be going over some more rules of differentiation, specifically the product rule and quotient rule. We'll also at the end apply multiple rules at the same time and see how they kind of stack on top of each other. So here is the product rule, and it states that if h of x is a product of functions, that is to say it can be written as f of x times g of x, then dh dx is equal to f of x dg dx plus g of x df dx. Okay, so you take the first, multiply it by the derivative of the other, and then you take the other one and multiply it by the derivative of the first. So in this case, h of x is equal to x to the 4 times cosine x. This is a product of two functions, x to the 4 and cosine of x. So to work out what dh dx is, we would simply write down it's equal to, say, the first, x to the 4, times the derivative of the second, d cos x, dx, plus the second times the derivative of the first. And in application, this is going to look like minus x to the 4 sine x plus cosine of x times 4x cubed, but I'll bring out the 4x cubed out to the front. Okay, so it's very simple to apply the product rule most of the time, as long as you know the derivatives of the functions you're taking products of. Similarly, h of x here is equal to e to the x tan of x, product of two functions, e to the x and tan of x. So if we want to work out this derivative, we'd take dh dx is equal to the first times the derivative of the second, d tan x dx, plus the second, tan of x, d e to the x, which is the derivative of the first. So this is going to be equal to e to the x. Now, derivative of tan of x is, of course, 1 over square root 1 plus x squared, if you remember that from the very first video in this series. Plus, now the derivative of e to the x is again, of course, e to the x, so it becomes e to the x tan x. And this is the derivative, and if we wanted to, we could tidy it up a little bit by moving the e to the x to the outside by factorization. Okay, so that's basically the product rule. One of the easier rules to apply. You just need to know it. It's the first times the derivative of the second plus the second times the derivative of the first. Now the quotient rule is a little bit messier to apply. It says that if h of x is equal to f of x over g of x, it's the quotient, or it's involves division in some way, and also g of x is not equal to 0. Remember, this is only relevant in the sense that if we want to evaluate the derivative at a point, then we need g of x to not be equal to 0 at that point for this rule to be guaranteed to work. Okay? So as long as g of x is not equal to 0 at the point we are trying to evaluate this, then we're okay. But it says that the derivative of this quotient of f over g is equal to the derivative of the thing below the line times the thing above the line minus the derivative of the thing above the line times the thing below the line. And that all has to be divided by g of x squared. Okay? And this isn't composition of g of x or anything like that. This is just g of x multiplied by g of x. Okay? So let's apply it to, for example, h of x is equal to sine of x over x. Well, therefore the derivative, dh dx, is equal to, I'll just tidy that up a bit, is equal to dg dx, so g is the thing below the line, so that's dx dx, times f of x, the thing above the line, that's sine of x, minus the derivative of sine of x, or the thing above the line, times the thing below the line. And that all has to be divided by the square of the thing below the line, so this is all divided by x squared. So this thing all tidies up to be dx dx is 1, so this is just sine x. So d sine x dx is, of course, cosine of x, so this becomes minus cosine of x times x. So this all breaks down to be sine of x minus x cosine x all over x squared. Okay? And just as a little, to be pretty careful, we'll say as long as x is not equal to 0. Okay? The reason this is important is because we want to ensure that in the initial statement, of course this thing doesn't make sense if x is equal to 0 intuitively, because we've got a x squared below the line. However, just to be very careful, technically speaking, g of x is x, so when x is equal to 0, g of x is equal to 0, so this rule is technically not allowed to be applied. Okay? So this formula is valid for all x except for x equal to 0. Similarly over here, we're going to apply the quotient rule to solve this one. Notice also that this is the actual inverse of our first function. I say that, I should say the reciprocal of our first function, to be clear. That is, it's just flipped upside down. And this is to show that the functions f and g are treated very differently by this function, basically. So dh dx is equal to, let's just look up the rules, it's the derivative of the thing below the line times the thing above the line. So it's d sine x dx times the thing above the line, which is x, minus the derivative of the thing above the line times the thing below the line. And it has to all be divided by the thing below the line. So it'll be sine squared x. And again, this of course means the numerical square of sine. So this becomes, this is a cosine of x, so it's an x cos x minus dx is again 1, so it's just minus sine x all over sine squared x. Okay? And this time, however, it's for x not equal to, say, n pi, for n being an integer, because these are all the zeros of sine of x. Sine of x is equal to 0 whenever x is a multiple of pi, at least assuming this is the radian sine function, which is usually what we deal with. Okay, so that's the quotient rule. And lastly, I just wanted to show an example of applying multiple rules. Okay, what do I mean by this? So here we got the function h of x is equal to x cubed times sine of x to the 5. So this looks like a product rule application, because our function h of x can be written as x cubed times sine x to the 5. So it's x cubed sine x to the 5. So great, we should apply the product rule. However, the issue is we don't know how to differentiate this function immediately. This sine x to the 5, if we want to apply the product rule here, we need to know dg dx and df dx. We need to know the derivative of the two things we're taking the product of. But we don't know the derivative of sine of x to the 5. However, we can use the chain rule, because this is the sine of the function x to the 5. So we can use the chain rule to work this out. And that's what we're going to end up doing. So let's just go through this a little carefully. So this means dh dx is equal to, well, the product rule says you take one of them and multiply it by the derivative of the other, d sine x to the 5 dx. And then you add on, you write down the other bit, sine x to the 5, and take the derivative of the bit in front. That's just the product rule, and it's always true. Now, we could substitute in this for 3x squared, but what do we substitute in for this? Well, we have to apply the chain rule to work it out. So this is equal to, well, I'll just write down this bit over here. This bit over here is going to be 3x squared times sine x to the 5. So we've got kind of this right-hand half worked out, that's fine. But how do we work out this? Well, it's still going to be x cubed. We'll have to apply the chain rule here. So this is d sine x to the 5. Maybe I should be using a little more careful notation here, just to be clear. Then we're going to differentiate dx to the 5, because sine x to the 5 is the sine of the function x to the 5. So this really is just the chain rule in action. Well, let's do a little more brackets as well. Dx to the 5 dx. So what this comes out to be is, remember, it's d sine of u du. So that means this will be cosine of u, or cosine of x to the 5. And this will be 5x to the 4. So this is equal to 5x to the 4 times x cubed, because we have the x cubed kicking around from before, times, well, rather, not sine, but cosine of x to the 5. plus 3x squared sine x to the 5. Okay, and if I'll just quickly combine x to the 4 times x to the 3 is just x to the 7. And this will be our answer. 5x to the 7 cosine x to the 5 plus 3x squared sine x to the 5. Okay? So hopefully that makes sense to you. And using these tools, we really should be able to differentiate any kind of function that's made up of easy to understand functions. But hopefully this all made sense to you guys. This was Connor Mead with the Calculation Center, and I'll see you guys next time.